Hiya. So this is a project I've been working on alongside my colleague Ben Tracy, and also Pablo Rebel and Julian Miller from Intel. And the history of this SYCL graph extension project is actually that originally both CodePlay and Intel had their own vendor extensions that exposed a SYCL dependency graph to the user. But after the acquisition of CodePlay by Intel, we decided to combine our efforts and work on a single unified one API vendor extension, which is what this presentation today is about. So I'm going to cover a bit of the motivation as to why we came up with this extension, give an overview of the specification, talk about a few implementation details, and then our plans for future work and really what we're working on right now. So SYCL is already able to define a graph of execution. A command group defines a set of requisites which must be satisfied in order for a kernel function to run. These requisites form the edges, the kernel functions and nodes, in a directed acyclic graph. But in the core SYCL execution model, this graph is implicit in the runtime as command creation and execution are tied together. What our extension does is it separates command creation from execution by giving the user explicit control of this dependency graph so they can define it and then submit it for execution separately. So what are the benefits of this, of separating command construction from execution? Well, for repetitive workloads where you're submitting the same pattern of operations over and over again, you'll need to pay that command construction cost once, and then you could submit the graph many times without having to construct those commands again. And also, because you've done the work of constructing that graph by things like compilation and working at the internode dependencies, when you do come to submit the graph for execution, you can do it with lower latency and get it onto the device faster, so you can tend to have better device occupancy from that. As well as this, optimizations also become available on that graph of commands you've defined. Things like kernel fusion between the nodes, and also more optimal memory allocations, because you can maybe work out when memory can be reused between nodes and possibly stay resident on device. So I've got a quick trace here to illustrate that. This is taken from a 1D heat example in a one API samples repo. It's using an older version of our graphs extension. Really, the thing to look at here is the GPU busy bar along the bottom that shows device occupancy. And when you're using a graphs extension, you have much better device occupancy compared to without it when there's gaps, when the GPU is idle, because you're waiting on the host to do the work of doing some scheduling or command construction before getting those commands onto the device. This idea, however, of separating command construction from execution isn't a novel one. It's in a lot of APIs already. Vulkan has command buffers as core. OpenCL has the CLKHR command buffer extension, which I talked about at IWOCL last year, if you're interested in looking up the video. And Level 0 also has a command list construct as core. And there's other APIs. CUDA has an analogous feature in CUDA graphs, but has the drawback of the vendor lock-in to NVIDIA hardware. So for doing our SYCL graphs extension, we envisage that you could use all of these APIs as your SYCL 2020 backend to propagate performance benefits and advantages of graphs through the stack. Our goals as a project as a whole is right now it's a vendor extension, one API, but ideally we'd like it to be a Kronos extension once we've basically got the extension mature enough to bring it to the SYCL working group. We also want to improve performance, of course, in particular for workloads that have small kernels and repetitive executions, because for the repetitive executions, then you're saving more in those command construction costs, and for small kernels, because then you'll tend to see the biggest benefit relative for the benefits in the overhead savings compared to if you've got very long-running kernels, then those long-running kernels are always going to dominate the performance of your application, regardless of how much you optimize away the scheduling. And the last thing I've got here is we'd like to ultimately support a lot of the frameworks that currently support CUDA graphs, things like TensorFlow, PyTorch, Chromax, and Cocos. We're not there yet, but that's an end goal we're certainly aiming for and have in mind. So that's a bit about the background. So I've got an extension, and now I'm going to give an overview of the spec itself. So the spec lives in a fork of DPC++, and we've been developing this for a while, but it's now a state where we've got a pull request up to mainline DPC++ for the first revision of it. It's still in the experimental state, which means all the APIs I'm presenting here are subject to change. But the good side of that is any feedback you have for us, we can action and we can make changes to to improve things. So please do leave feedback either as a comment on the spec PR or even just an issue on our DPC++ fork if it's a more general comment. And this is probably the first revision while still in the experimental state. Well, we've got plans for a second revision while still experimenting with things. And I'll talk about that in our future work slide. So on to what our spec's defining. So if we just think back to that motivation, what we want to do is take that implicit graph that's in the SYCL runtime and turn it into a graph that's explicit to the user and the user has access to. And in order to do that, we've defined a new class called command graph. And this can be in one of two states, a modifiable state where commands are added to the graph and you build it up, and then an executable state where it's actually ready to be submitted to the device with relatively low latency. And the transition between the two is called finalize. We've templated the class in order to illustrate these two different states. So this strong typing makes it clear to the reader of the code what state the graph's in without having to query it. It's also consistent with the SYCL kernel bundle design. Another thing I'll point out is that right now we pass a device and a context to the command graph and you construct it. So in our definition of what a graph is, a node is tied to a particular device. It's not device agnostic. And we currently have the restriction that every node in a graph has to be tied to the same device. And we enforce that by passing that device on graph construction. We do have plans in future of potentially having a graph of devices targeting different nodes, and that could potentially change this API. So that's why we're still in the experimental state, because we've got plans to do things like that. But this is how the command graph class looks for now. So a bit more about that transition. So the model we expect for usage is that adding commands will be synchronous and relatively cheap, because we want as much work as possible done by the runtime in the finalize step. So that's where we want things like compilation to happen, building up your SYCL 2020 backend representation, optimizations in that graph. So that's where we want to be a kind of single point of overheads as much as possible. And the user can create multiple executable graphs from a single modifiable graph. And each one of those executable graphs has a fixed topology of commands and can be submitted for execution. It can be submitted for execution many times, but right now we also have an additional restriction that you can't submit a graph for execution while a previous instance of the same graph is still being executed on device. I'll talk a bit more about why that exists and how we're hoping to relax it later on. This is how you actually submit an executable graph to run. We've got a new method on the handler, ext_1API_graph. This is nice because you can use handler depends on to express the dependencies of that executable graph submission. And you can also naturally build up nested graphs. So when you're adding command groups to your graph to build up the nodes, if you use handler ext1API graph with another executable graph, that gets added as a child graph or subgraph as part of the larger parent graph. And that's something that's quite natural to do just with this method of expressing executable graph submission. Okay, so on to how we actually add the nodes to our graph. So we provide two different mechanisms for doing this. We'll call them queue recording API, also known as record and replay. And we've got an explicit graph building API. So previously, when this extension was two separate vendor extensions by Intel and CodePlay, we each only provided one of these mechanisms. But since unifying, we now provide both. And that's good because each is really useful in its own particular set of circumstances. So by providing both, we give the user a choice as to which one of these to use. So the queue recording API introduces state to a SYCL queue. I mean, a SYCL queue is in the recording state rather than the command submitted being submitted immediately to the device. They're redirected to the graph that's being recorded. And by submitting commands as you would to the queue, that's how the graph is built up. And this is nice in the situation where you've got a large existing code base that you want to port, because you just bookmark it and can begin and end recording entry points. And it's also useful if you've got an external library you want to record to a graph where you don't have access to the source code to modify it for a different API. On the flip side, we also have an explicit graph building API where the user directly builds up the graph by explicit methods to be provided in a modifiable graph to add nodes and then add the edges. And this is a bit more expressive and powerful, easier to debug. And it's also less likely to trigger the kind of invalid usage cases you could get just by using the queue recording API. When you add the nodes and edges themselves, nodes always correspond to command group submissions, but there's a few different ways you can add the edges. There's two provided by the core SYCL spec right now, and there's two provided by the explicit graph building API. ones from the core SYCL spec is that buffer accessors and the dependencies expressed by those we recognize as edges. If you use handler depends on and pass in an event that was returned from a queue recorded node, then we recognize that as an edge. And the explicit API, when you're creating a node, if you can pass some dependent nodes that correspond to edges, and we've also just got an explicit make edge method. So in order to actually illustrate these to make them sink in better, I've got an example here that I'm going to modify to use various of these APIs I've just described. To make things clearer, I've chosen this example purely because it can fit in a single slide rather than because it's interesting or relevant in some way. So it uses a USM memory, and the first node initializes the memory, and then the second node does a SAXP computation on it. And there's a single edge here that's represented through the handler depends on, and you pass an event that's returned from the first node, so it recognizes that as an edge. So how do we put this to record and replay, first of all? Well, first thing we need to do is define our command graph object. And then we've got the same queue submissions we had before, and we just kind of bookend them and begin recording and end recording. And that means that these commands are redirected to the graph to add them as nodes. And after we finished recording, we know there's not any more commands we want to add to our graph. It's ready, so we can finalize it into an executable graph, and then submit it for execution using our new handler method. And that's really it. It's relatively easy to port the code. Handler depends on corresponds to that graph edge because we know that init event was returned from a node we created during queue recording. So we identify that as an edge as it's passed into a node we use in the graph. If we were to try and wait on init event or try to query its profiling info or command status, all those things would throw an exception because they don't make sense in the context it's used. Likewise, if we tried to pass in a regular SYCL event from outside the graph into a handler depends on inside the node we're creating, that would also be an error. So that's record and replay. I'm going to show a couple of the explicit API methods. So here we've got rid of the begin and end recording, and instead of queue submits, we've got a method on our command graph that adds a node, and it adds the command group, and then a list of properties. And then we've got very similar command group submissions, but not the same because we no longer have handler depends on because we don't have an event anymore. Instead, our graph add call returns a new class we've defined called a node class. And the way we use these node classes is that with a property list parameter, we can pass in a list of nodes that this new node we're creating depends on. So we can pass in the init node here to say we want this compute node to depend on the init node. And that's how the edge is now expressed. We do also provide a empty node API that doesn't have the command group function. It just can be used to say provide a list of dependent nodes. So that's equivalent to an empty node and can be used to marshal some dependencies. That's useful. And then finally, I'm going to talk about make edge. So here we've got rid of passing any properties to property lists. So if we didn't have make edge, then it wouldn't be defined how the order in which these two nodes would run. But by doing make edge, we say create an edge and that has to happen before compute. And this API is interesting because it's actually possible to create a cycle with it. So if we had another call to make edge after the one we have here, and you just swapped around the two parameters, then create a cycle in our graph, which breaks our definition of this being a DAG. So the runtime is currently specified to throw an exception, in this case, for make edge. You can disable this if, as a user, you're using this function and you know you're not going to create a cycle. We have a property, you can pass the property list on command graph creation, they'll turn off this error checking. But having make edge at all is useful in multi-dimensional applications, like stencil applications, where maybe the order in which you're adding the nodes could be different from the order in which you want to create the edges from. Great, so that's you kind of try to fly through the expansion spec, and I'm going to talk a bit about the implementation details and where we are today. So our implementation is in DPC++, not the same fork that I linked to earlier. Right now, the main things that work are using kernel commands for nodes, so like parallel for single task, using USM memory of those. Both the command construction methods I've talked about implemented. We also have a level 0 backend that works, and although we are definitely interested in other SYCL 2020 backends, this is just the one we prioritized for getting things kicked off. So there are some limitations about this and some things we're working on, which I'll talk about in the future work section, but This by itself is enough to get some simple real world code running. So one DNN is a performance library for deep learning that in the one API stack. And we've got the SYCL interrupt USM sample working just using this patch here, which kind of illustrates the benefits of record and replay, where this is like a call into a library. We've been able to capture it in a graph just by kind of bookending it in graph begin recording and end recording. And now we've got our graph. How does the implementation map that down to hardware in a performant way? So DPC++ has an implementation detail called PI or PI. That's an abstraction layer that's implemented by SYCL 2020 backends. We've extended this interface in a very similar way to how OpenCL is extended by the CL-HR command buffer extension. So we've added extra entry points to PI and some new command types that represent a command buffer, which is essentially similar to a graph, but it's in lower abstraction level. So you define it ahead of time, you add commands to it, and you submit that block of commands to execute. There's not a one-to-one mapping of a SYCL graph down to an underlying PI command buffer. It could be that a SYCL graph is partitioned into several underlying command buffers if the runtime needs to do that, possibly on, say, a host task. It could have PI command buffer, then your host task implementation, then another PI command buffer to kind of partition your graph. So we've implemented our new PI entry points for level 0, but for the backends we haven't got around to implementing yet, we did provide an emulation mode where we just implement our graph API by reissuing the commands using the existing PI entry points. So that still enables correct execution, but just not quite as performant through the stack as where we'd like to be. So I'm very quickly going to cover the additions and the mapping. So really we define a new type for a command buffer, create entry points, finalize, and queue. I think the only interesting thing to point out here is that right now the only command you can add to a PI command buffer is a kernel execution command. Other APIs have things like memory copies, fills, the same for images, barriers, but we just have a kernel for now really because it's not just on the critical path in order to getting a working prototype up and running. This is the thing you absolutely need. And as we test with more applications and our implementation matures, envisage us adding more things here. But because we have the flexibility to modify things, right now we've just got a kernel command. And this is how it maps onto level 0, which is what I've implemented right now, and how we imagine it mapping onto command buffers and CUDA graphs once we get around to implementing those SYCL 2020 backends, which we haven't yet. Mappings are fairly straightforward, but I imagine the difficulties in actually mapping things will be as in the behavior of what you can do with the underlying command buffer in the different backends. For example, there's OpenCL command buffers has a property called simultaneous use, which is when you can submit a command buffer to execute while a previous instance is still running. So I mentioned before in SYCL graph, this is something we forbid. And the reason for that is it has different behavior in different backends. So right now it's easiest just to ban it, but it could be that we work around this by in underlying backends that don't support it by doing smarter scheduling. But that's the kind of thing that could be more tricky when implementing this mapping onto different backends rather than just the pure mapping of what does each command buffer and type map up to. So I've got a final slide on implementation here. I'm just going to touch on a couple of interesting points relating to how nodes and edges are implemented. So nodes, when we implemented our underlying like detail class and implementation, we first of all just stored a command group function there. But then we worked out that some variables that were being captured were going out of scope by the time it came to like process it. So instead, we fixed that was we got the handler to process the command group first, and then our node implementation just extracts the relevant information from the handler and stores that. And as part of doing that change, worked out we need our definition of a node to be device specific because the handler can often use device specifics it normally gets in the SYCL queue to do this. So for example, when implementing reductions in DPC++, that you can use device workgroup or subgroup size for that. So we kind of need that device information in order to be able to do this. For edges, our implementation of edges bypasses the existing DPC++ scheduling. The only time we use that is when we're submitting our executable graph to run. When we're mapping our edges, actually what they correspond down to is a new sync point type we've got for command buffers. It just expresses the dependencies within a command buffer. Or when you're partitioning your SYCL graph into multiple command buffers, then the PI events that are returned from command buffer submissions can also correspond to edges in those cases. So on to future work. So really what we're working on right now, I speak, is trying to complete our implementation to the spec revision 1 that we've got the PR up for. So there's some things we need to do to get there. We've got an executable graph update feature as part of the spec, where you can update the inputs and outputs of an executable graph. If anyone's familiar with the OpenSYCL Mutable Dispatch command buffer extension that was provisionally released the past year, you could use that to implement this by changing the arguments to a kernel command. We also need to have some work to ensure that buffer accessors correctly form edges. So that's why right now you can only really use USM. This is actually tied up quite a lot in the existing DP++ scheduling, is proving a bit tricky to refactor. So I think that'll be one of the main challenges to get this work implemented nicely in a way that's acceptable, say, upstream. And also not all command group functionality can be captured in Node yet. So most parallel forwards will work, but if you want to use things like host tasks, cycle streams, specialization constants, we've not even started kind of looking at those yet. And we also want to do work on a follow-up specification release. So right now we've got revision 1 that we're hoping to get merged very, very soon. It's been open since, I think, February 2022, so it'll be a good moment once that actually gets merged. But things we've started talking about but haven't had time to come to a conclusion on are graph-owned memory allocations. So this is when the lifetime of your memory allocation maps to the lifetime of your executable graph, and that's the scope in which the memory is valid. And that lets you do some quite interesting optimizations and possibly avoid having to do the memory allocation at all if you can work out that the data can stay resident on device in a different way. We also want to look into a single graph, the nodes targeting different devices. So in that, right now, if you've got a multi-device platform, you have to have different single device graphs and then compose them using, say, SYCL events. Whereas ideally, you'd have one multi-device graph and then just have the internal edges of the graph correspond to the dependency between the different nodes. And actually, just before IWOCL, there was an OpenSYCL spec release, which included the command buffer multi-device extension, which could be used to implement this. And finally, I've put here the point about being able to have more than one instance of the executable graph submitted by the user at once, and trying to get the SYCL runtime scheduling work so we can work around those backend differences. Like that in the next version of the spec. And finally, and perhaps most excitingly, we're looking to merge with the kernel fusion extension, which is conveniently the next talk up at IWOCL this year. So look forward to that. So just to summarize, I've presented here a one API vendor extension that separates command construction from execution by giving user access to the dependency graph. The benefits of this are that it removes the redundant command construction overhead for repetitive command sequences. It reduces the actual latency when submitting the work to the device, and it provides optimization opportunities across the defined graph. So thanks very much for listening. Are there any questions?
Hi, is it possible to make multiple common graphs and then link them with edges?
So I guess you can nest graphs as in you have an executable graph and then add as a node in the other one, and you can submit multiple executable graphs, but then you're just using regular SYCL events to join them up rather than actual edges in the graph. So yeah, you can have a graph and add it as a node inside the larger graph by adding an executable graph as a node to a modifiable graph. That makes sense.
Yeah, thank you.
Yes, the way that's implemented isn't particularly smart right now. It just kind of expands the nodes into the larger graph rather than having some underlying like secondary command buffer in Vulkan or something like that. It's a bit naive.
More questions?
Are there any plans to serialize graphs to disk so they can persist between application runs?
I know you're a big fan of that for safety. There's no plans right now. It is something we have had in mind. I think the problem is it's always just been other more important things to work on in terms of just getting the core feature working of creating a graph of commands and then running it, and just really nailing that, I think now is the priority, but that is something we are interested in exploring in the future. Yeah.
So even if you're running two different parallel streams and two kernels in parallel, it might sometimes matter which kernel you submit first. So if you submit a very large kernel that occupies almost the same, almost the entire device, and then in another stream, another kernel, it might not launch until after the first one finishes, even if the kernels are independent. Are you planning to make some optimizations around this for the graph after it's built? If the kernels are independent, and if you already captured from some graphs runs the runtime information of how long each kernel takes. So like runtime JIT, not quite JIT, but yeah, runtime guided optimization.
Yeah, that's something we've not thought of, but it's an interesting idea. I think that's what's cool about this extension. It does enable a lot of optimization possibilities. I've kind of brought those in mind, but I think without trying to like get too far ahead of ourselves, just try and get this feature out, because a lot of people have been asking about it and are interested in it, and it's probably taken too long already to get to this point without kind of thinking too far ahead of optimizations. But yeah, that would be good. More questions?
So the way that SYCL thinks about queues is that they are already basically graphs.
Mhm.
So I'm not 100% convinced that such a new API surface is necessary. For example, what is such a graph than a queue that basically has a different flush behavior than a regular queue, which, for example, then in its destructor constructs the graph and returns some handle to re-execute the queue. Have you thought about something like that?
So I guess that idea uses it is not clear where like the end of like the graph would be. So I guess you're trying to find that ahead of time. So I guess we've tried doing a lazy queue property before, and it ran into issues. That's something we could take a look at if we chat to you offline about it. It sounds like a good idea.
During the panel yesterday, we were talking about SYCL trying to avoid a plethora of vendor extension, and maybe are only implemented by one single vendor.
Yep.
And to avoid basically what happened with OpenCL. So I was wondering what do you think if would be the right approach in SYCL? Because the next day I see vendor extension. So would it be better to first discuss the specification or propose specification and then go with extension? Because it seems that this is what happens in OpenCL.
So I guess in terms of getting things into the spec part of it, as well as you want to make sure you don't have something in the spec that is implementable and is backed up. So I think doing it as a vendor extension first, and then getting the implementation experience, and then bringing it to the working group, seeing something, that's work is then valuable to help people get the feedback on. I guess, like, to be honest, even last week I was making API breaking changes to this, and I think if I was getting lots of other vendors of time in their hands at implementing it and then changing the API every week, I don't think that's particularly like helpful workflow for them. So I think trying to get like at least a first revision or like second revision out there, and then saying this is something that works to the working group. Now, how do we want to listen to the standard either as a KHR extension or part of the core spec is a quite a good way to go for now. Is I think saying it's probably something that's maybe arguably overdue based on how long the discussions have been going on, because before I've started working on this, I've heard discussion about it in Codeplay. So for now, if a vendor extension is the quickest way to getting something out there.
I will try to help also answer that question with more context. You don't want, so vendor extensions are fine as long as they're open to the public and everybody can comment on it. But you also, and it also avoids the opposite end of committee work, which is designed by committee. So if you try to do everything in committee, you end up generally with a bad design. It works. The try and trust workflow that I've seen in all the other consortiums is you start with a small group, they work together, develop some features, make sure they flesh out most of the issues, and then when they reach a point where they have questions that can no longer be answered unless they see the bigger group, then it gets exposed to a bigger and bigger group. That is a good way for the workflow to work. Otherwise, if you always do everything in committee, you get designed by committee, and it's usually terrible. Okay, but at the other end, as long as you have multiple people working on it, and it's open, so everybody can examine it and start pitching in right away. And this is all on open GitHub, right?
Yeah.
So I personally like this direction, okay? And the way it works after this is you're going to be exposing it to a larger group and then a larger and larger group, and each group now adds their input, and it's less chaotic that way, I think.
Okay, I think in the interest of time, we'll move on. So we'll thank our speaker.
Thank you.